All right, we're going to start on differential equations today. Now, you've been doing differential equations actually for a while, just very basic ones. You know, dy dx equals this, and then we change it to y equals. But essentially, you're solving a differential equation. So all sorts of things use differential equations. So some examples. Now, it might not look like what you're used to seeing, but that is actually the Newton's second law of motion, force equals mass times acceleration. It's just written as a differential equation, where force on the right-hand side there we're saying, well, that's some function of x, force, is equal to mass, there's your constant, times the second derivative of displacement with respect to time. Well, that's acceleration. That one you probably don't recognise, but that's the formula that controls a shock absorber. So it's a damped oscillation. So it ends up being like a sine curve combined with an exponential curve. So as it goes further and further along, the amplitude gets smaller and smaller and smaller, which is how a shock absorber works. That one there should be very familiar to you right now, because that is the predator-prey equation, which is exactly the virus curve that they've been looking at, is the classic one of those. So all those sorts of things are basically called differential equations, equations that involve derivatives. The order of a differential equation, you simply look for what's the highest derivative. So the first one there would be a second order, the second one's also second order, and the third one there is a first order. Now in our course, we're only going to be looking at first order differential equations. So how do we solve them? As I say, we've been looking at it so far at a very basic level, and it's simply integration. So the general solution of a differential equation, well, that's like an indefinite integral where we've gone plus a c. And so you get a family of curves. So you get the same basic shape, but depending on what the constant is, you shift it up or down on the number plane. So you get a whole series of the same shape. Whereas a particular solution is like our definite integral, where we have some sort of initial conditions that we can sub in and work out the particular constant for that situation. And so we call it an initial value problem. But it's the same as saying, what's the initial conditions? Okay. So here is an example of one. X times dy dx plus y is equal to 0. Now this is why when we were doing integration, I was always saying, don't mix your variables. Okay? Because what we want to do, it's an equation. You're solving an equation. So what you do to one side, you do to the other and things like that. So what theoretically I've done before I've integrated is I've separated them. So on the right-hand side, I've ended up with, dx divided by x. And on the left-hand side, I've ended up with minus dy divided by y. Then I'm saying, well, what I do to one side of the equation, I do to the other. So I'm going to integrate both sides. And so we get minus the log of the absolute value of y is the log of the absolute value of x plus a constant. And so using my log laws, I can now recombine this. I get the log of xy, or absolute value of xy, is negative k. So xy, or the absolute value of xy, is e to the minus k. But e to the minus k is just a constant. Because remember, k was our constant I've added on there. So y equals a constant divided by x. So there's graphs of several different solutions of that one, so different general solutions. Basically, we're looking at the hyperbola. Now, if they then gave me the initial value problem of that, well, when x equals 1, y is 1, I could now sub in and work out, the constant is 1. So the particular solution is y equals 1 on x. But essentially, it's still just integration. Okay. So first of all, we're going to look at what we call linear differential equations. There's my definition for linear. So you could have several derivatives, but every derivative is multiplied by a function of x, and not necessarily the same function. So that's why I've gone a naught x, a1 x, and so on. They could be different functions of x. And of course, it could equal a function of x as well. But remember, I said we're only going to be dealing with first order ones. So we won't be going up to the very high order derivatives. So we want to look at first order linear differential equations. So basically something like that. So y dx plus some function of x times y is equal to some function of x. So it's in that form. If the right-hand side equals 0, then basically it's simple, straightforward integration. I've just got to rearrange it, and I'll get it into something that I can handle. If it's not, that's when it becomes much more fun. We multiply the whole equation by what we call an integrating factor. And that factor is e to the power of the integral of whatever that function is in front of y. So we work that out, multiply the whole equation by that. So let's have a look at this one. The derivative plus 4y on x is equal to 3x squared. So I've got to work out the integrating factor. Well, the integral of that function that's multiplied by y, in this case 4 on x. If I integrate 4 on x, I get 4 log x. Don't worry about the plus a constant. So my integrating factor will be e to the power of that. Well, e to the power of 4 log x, I can change the 4 log x to be log x to the power of 4. The e to the log cancels, so I'm just multiplying everything by x to the power of 4. That is now what I'm solving, and that's a lot easier. Now you might not see it straight away, but on the left-hand side, we actually have a product rule. Write down the first, diff the second, plus write down the second, diff the first. So on the left-hand side, we actually have the derivative of x to the power of 4 times y. So let's call it that. It's the derivative of x to the power of 4 times y. So I will now integrate both sides with respect to x. Well, integrate the derivative, it just comes back to the original function. So the left-hand side is x to the power of 4 times y. And on the right-hand side, we're saying 3 times the integral of x to the power of 6. Add 1 to the power over the power, plus a constant. But if you do want to make y the subject, well, clearly all you've got to do is divide by x to the power of 4. We'll have a look at this one. Not immediately obvious that that's a first order linear differential equation, because it doesn't look like it's in that pattern. But if I play around with it, split my fraction, becomes y over x plus 1, move the y over x to the left-hand side, and it's now in that form. It's y dx plus some function of x times y. In this case, that function is minus 1 on x. And on the right-hand side, equals some other function. Well, in this case, that's just the constant number 1. So now let's go find the general solution. So y dx minus y on x is equal to 1. Work out the integrating factor. So the integral of minus 1 on x dx is minus log x. So I have e to the power of minus log x, which is the same as e to the power of log x to the minus 1. E to the log cancels, 1 on x. So I multiply everything by 1 on x. On the left-hand side, I've now created the product rule. So that would be dy dx, sorry, not dy dx, d dx of y on x. Now how do you get it real quick? Basically, it's your integrating factor times y. Now, if you go back and look at the last example as well, you'll see it's the same thing. Integrating factor times y. So integrate both sides with respect to x. I now have y on x is log of x plus a constant. So y is equal to x log x. Here's where it gets a little bit interesting. It's no longer plus a constant. It would be equal to plus some constant times x. So we've multiplied both sides by x. So we have the derivative plus 3y is equal to x. I work out my integrating factor. This time e to the power of 3x. Can't simplify that, so that's what I'm going to multiply by. E to the power of 3x. Much more interesting. So that's going to be d dx of y e to the 3x equals x e to the 3x. Integrate both sides. Now, I've put this example in, but if you think about it, you're not going to get this question in extension 1. Because to integrate the right-hand side, x e to the 3x, I'm going to need integration by parts to do that. And that's an extension 2 technique. So let's do it. So u will be x, du will be dx, dv is e to the power of 3x. So we get uv minus the integral of v to u, and then we'll divide everything by e to the power of 3x, and we come up with our answer. But as I say, extension 1 wouldn't see one like that, for obvious reasons. Okay, so let's play 13a. Oh, it's all rhymed.